As amazing as the first image of the black hole was, the lack of a discernible swirl was disappointing compared to those artist renderings we're used to. Let me explain resolution, the Rayleigh criterion, and suggest some future improvements to the way we view the universe. We're used to describing resolution in terms of pixels on a screen, but astronomy defines two different types: spatial resolution of images and angular resolution of telescopes. Spatial resolution is the smallest discernible detail in an image. Finer spatial resolution means a sharper image. Angular resolution is a line-of-sight limitation of a telescope to discern details. It is constant no matter the distance. Spatial resolution is the angular resolution of a telescope in radians multiplied by the distance. The extreme distance to the black hole is why it's so blurry. So the smaller the angular resolution of a telescope, the finer the image. Introducing the Rayleigh criterion, which gives the theoretical minimum angular resolution of a receiver. It's proportional to the wavelength and inversely proportional to the receiver's diameter. So the larger the receiver's diameter and the shorter the wavelength, the sharper the image. Theta is the angular resolution in radians. D is the receiver's diameter, and lambda is the wavelength, both in meters. The constant 1.22 represents the position of the first dark ring surrounding the central Aries disk of the diffraction pattern you get when you shine a light through a circular aperture. This plot of Aries disk's light intensity shows it better. Mathematically, it's the first to zero of the order 1 Bessel function of the first kind, j of x, divided by pi. This works for single-dish telescopes, but what about arrays? It works for these too, if d is redefined as the baseline length between the two most separated dishes of the array. So an array has the same resolution as one giant dish of the same size. In telescope arrays like this, the dishes are connected by wire as elements of a larger antenna. But to image a black hole, you need a telescope almost the size of Earth. Enter Very Long Baseline Interferometry, VLBI, a method of taking data collected at various telescopes and digitally combining it to make a single image. That's how the Event Horizon Telescope imaged the black hole in M87, using a network of radio telescopes around the world to create an Earth-sized array. To improve this resolution, we have to reach beyond Earth. A radio telescope array in Earth orbit has been proposed. This would have about 5 times the resolution of the Event Horizon Telescope. For an even greater improvement, I propose we put a constellation of telescopes in both ecliptic and polar orbits of the Sun. A solar orbiting radio telescope array, SORTA for short, could have a baseline of at least 300 million kilometers. At the black hole in M87, this array could discern details starting at about 2 to 3 times the size of our Sun, or several thousand times smaller than M87's event horizon. Being able to resolve astronomical phenomena in this detail could give us clues to the nature of dark matter, and puts direct imaging of exoplanets within reach.